Hello, Vest Scholars, and welcome to this discussion of weather. We all experience weather on a daily basis. One day it's raining, one day it's sunny. And of course, weather is given to us or weather forecasts are given to us by meteorologists. Meteorologists make weather forecasts based upon data that they have that's historical, from instrumentation spread all over the place, and of course, from satellites that NASA maintains as a part of its Earth observation network. All these things together actually make weather forecasting these days a whole lot more accurate than it was in the past, even though perhaps your grandparents may say that the meteorologists of the past were a whole lot better. Well, that's all anecdotal. The reality is that, it's important to keep in mind when a weather forecaster says that that there's a particular probability of rain, 20% chance of rain, for instance, that just means that 20% of the time it rains when the conditions are like this. It doesn't mean it's going to. It doesn't mean it's going to rain 20% of the time. It's important to keep these things in mind. They're all based on probabilities because the atmosphere and the movements of air and the movements of energy are very complex. And as we've talked about at other times, these complexities make it very difficult to create models that are going to be 100% accurate all the time. So it, again, comes down to probability. So brought to you by the atmosphere, the geosphere, and the hydrosphere. I should throw the exosphere in there as well, because that energy drives all of this. Let's learn about weather. So here, it's important to remember that weather is driven by energy from the sun primarily, which drives the hydrologic cycle. And of course, it's important to keep in mind that this hydrologic cycle is really focused on the interaction between the atmosphere and the oceans and other bodies of water as well. And then, of course, if the Earth wasn't rotating, the winds would move very differently because we wouldn't have the Coriolis effect, which is the deflection of wind patterns based on the rotation of the Earth. To observe the weather, we use, and you guys have been learning about these for years. We use various instruments here on the surface, and these include, of course, things like thermometers and anemometers and so forth that help us to measure current conditions with various things: temperature, humidity, precipitation, and so forth. Now, these, of course, have to be, when you put these out, there's certain rules one should follow to get accurate readings. There's a lot of variables that are involved here as well. So the correct placement of an instrument is very, very important. Likewise, above the Earth, NASA maintains a very large fleet of Earth observing instruments. So all of these satellites have one or more instruments on them that are taking measurements of various aspects of the Earth system. There's even a couple more beyond this that aren't listed on this page. But each and every one of these bits of the Earth observing constellation that's out there provide meteorologists, scientists, and others, and of course you, when you check the weather forecast, with invaluable information. And this is one of those key pieces of information bodies of information that keeps society thriving the way that it is. And some of this information, of course, comes in the form of cross sections of the atmosphere, such as with this particular system here, Calypso. And here we're going to be looking at an extra tropical cyclone in the Northwest Pacific. And so you can get some really great data. You can see the flight pattern that the satellite was taking over the Earth at this time. And then, of course, as that flight pattern occurs, it's looking at echoes within the atmosphere at various levels of precipitation. So it's the light bands that it's using are bouncing off of the particles of water in the atmosphere. So this kind of subtle information is a whole lot more detailed than we had in the past. And so, that level of detail provides many other levels of complexity, but it also provides a whole lot more accuracy. So these things are really important. All right, and of course, this allows forecasting to occur. Forecasting is done using models, and the models are created using various parameters, taking various parameters in mind. And of course, some of these parameters are more unique to North America than they are to Europe. So you'll hear names like the North American model or the European model and so forth. These are based on assumptions that are indicative of particular regions in some cases. And sometimes the European model gives a different forecast than the North American model, and that's okay. And sometimes one's right and the other's not. That's normal. It's this modeling does allow us at various levels of the atmosphere, because it's not just what's going on at the surface, it's also what's going on at various pressure levels in the atmosphere, allows us to create a picture of what's going on, and then, of course, predict what's going to happen or what we think will happen probabilistically in the future. So, of course, these models are also dependent upon not only professionals, but also networks of volunteers. You can, of course, install a weather station at your home, and you can actually become part of a weather monitoring network through, say, Weather Underground or some other organization like that. And that information is also invaluable because that's a good way to get involved in citizen science. All right, the oceans, of course, are very important for weather. They are, on some level, the thing that drives it from below. If the sun drives the weather from above, the oceans, of course, which are warmed and unevenly heated by the sun, also, of course, then also subsequently drive the weather from below, because they are such good absorbers of heat, and, of course, because they move that heat around via ocean currents. Okay, so there's the gas exchange part that's always occurring between the atmosphere and the ocean through the hydrologic cycle. There's also the fact that the oceans are dark in color, so they're absorbing a lot of heat. And then, of course, there's circulation within the oceans, thermohaline and then surface currents and so forth, that move that heat around. And so what you're seeing here, of course, is a false color image of the Gulf of Mexico. And you're looking at a very, very warm Caribbean and a much cooler Gulf of Mexico. There's Hurricane Katrina and Hurricane Rita. And you can see, and it's showing you how during these hurricane tracks, they came through and hit warmer pockets of water, which provided fuel to those storms. And those are two very big storms. All right, so global winds, of course, we know that air is going to rise when it's warm and descend when it's cool. And so that happens at the equator. We call that a Hadley cell, where at the equatorial regions, the winds will rise because the air will rise because it's warm. And then, of course, it'll move along the upper part of the troposphere and then descend back down as it cools around the subtropical high region at about 30 degrees latitude, and then move its way back down to the equator. This Hadley cell is also mimicked on the other side of the equator. Then there's also the mid-latitude westerlies and of course the down here as well in the south, the same thing. Oh, sorry, down here the same thing between 30 and 60 north, and then from 60 to 90 north and 60 to 90 south there are the polar easterlies, and of course these are all driven by temperature differentials. Now, if we rotate the Earth, these convection cells get deflected. And I should have pointed that out before I started mentioning westerlies and trade winds and things of that nature, because otherwise these winds would just pretty much travel north and south, and that's it. But they don't just travel north and south. So if you think about explorers, or let's just take North America here. Take Virginia. Take our Virginian colonies at a time before the Revolution, when trade was occurring between England and here. People would sail their ships back using the mid-latitude westerlies. We're 38 degrees north, and so conveniently, ships could travel from North America to England relatively easily because of the westerlies. Those would blow the ships by default back towards Europe, and they'd have to travel a southern route down to the Caribbean before making their way back up the coast. And so it wasn't unusual at all for ships at that time to travel back from, say, New England or Virginia directly to Europe. And then to come back from Europe, they might have to travel to the Caribbean first and then make their way up the coast towards Virginia and so forth eventually there. So they might stop at their colonies in Jamaica and other places where they had plantations and then make their way up the East Coast. So, of course, these winds have been very, very important in shipping over the years, of course, until steamships were developed, and then once steam power was invented and subsequent propulsion technologies. They're still important because they drive storms, and of course, storms still affect all of this. But they provide the prevailing winds that are necessary for these things to happen. Local winds are important. We can have land breezes and sea breezes. Land breezes, of course, are a result of the accumulation of warmth and the re-radiation of long wave radiation from the land during the day, which then ends up causing the air above the land to rise, and then the air coming out from sea blows in, so you get a sea breeze. And at night, the opposite occurs. That will reverse there. So there's a moment in the evening when this begins to reverse at some point, or in the early part of the night. And that's good to point out. So that's typical along a coastal area on the east coast, the west coast of the ocean. Because the ocean temperature stays the same largely during these, during the entire 24-hour period. It's the land surface and its change in temperature that really affects this local wind pattern. Now, the ocean, of course, is complex. The ocean comes in a variety of layers, and depending on how deep you're talking about, of course, the vertical exaggeration on this image is high. So, but anyway, we're looking at layers of the ocean that are determined by temperature and pressure changes as you move from the surface down to the abyssal region and then eventually the hadal region, the trenches. We don't have any trenches off the east coast here in Virginia, but we do have, eventually you get to the abyssal pelagic zone where the deepest portions of the ocean lie between here and the mid-Atlantic ridge. Most of the time when you're at the beach, you're hanging out in the epipelagic zone, the very tippy top of that, well above the wave base. The wave base being somewhere above here. And that's the most turbulent part of the ocean. That's where most of that energy is being exchanged with the atmosphere. And then, of course, below a certain point, there's not as much interaction with the atmosphere except through deep ocean currents. So, of course, we can talk about the changes in temperature in the ocean. We can talk about changes in density within the ocean, of course. And then we can talk about changes in salt content within the ocean. This is salinity here. And you can see that each of these has variations. So density increases while temperature is decreasing and salt is decreasing as you get down into the depth of the ocean here. And then as that happens, there's major changes, of course, from the surface to the bottom. But they do kind of level out after a while, and there's not a lot of change. And so you can see here that this top portion of the ocean layer is much has a much rapid change that's going on. And of course, that's a result in part of that heating from the sun and the moving around of ocean currents and so forth. Part of that, of course, is the evaporation of water, which tends to actually increase the salt content of the surface. All right, so this is looking at the Aquarius mission specifically, which is one of NASA's satellites, and looking at sea surface salinity. So this is something that we can explore with satellite as well. And so I've got the sound turned off, but I'll let it rotate a little bit. You can see areas where the red are red, where the salinity is high, and areas that are blue, where the salinity is lower. Okay, and so you can see there's even during the time periods represented here, and you can see the polar ice caps growing, so you can tell roughly that this is going through the period of an entire year over and over again. There's quite a bit of fluctuation in sea surface salinity that's seasonal, and that's a really important part of the Earth's the ocean's interaction with the atmosphere. All right, so the thermohaline circulation, I'll show you another NASA image here, can be modeled also using can also be modeled, and we'll watch this video here again without sound, and you can see the movement of surface waters and depth and waters at depth. Here we have the one you've heard of called the Gulf Stream, which carries warm waters from the Caribbean area up towards England and so forth, keeping Iceland and keeping England from freezing over, if you will. And then once it gets up to the Arctic waters, it will actually descend back into back towards depth and then travel along the bottom. Now, this is the velocity of these vectors is greatly exaggerated for the purposes of this, because this water can actually take a fairly decent amount of time to move around. But you can see this is sometimes called the ocean conveyor belt for a reason, because you have these currents are conveying water, and the water, of course, is changing in its salinity and its temperature. Colder waters tend to be more dense, and so they'll descend and so forth, and it occurs down around the South Pole as well. This also tends to connect the waters across the planet, including through the Indian Ocean and so forth. So all the oceans are connected through these currents. And of course, a really cool experiment was done once with this, or that wasn't an experiment done on purpose. It was a load of rubber duckies that were accidentally deposited into the ocean. And as a result of this, of course, ducks kept making landfall all over the place. And so it was a great illustration of how the ocean surface currents work, because here you have ducks ending up in Sitka, Alaska, Hawaii, Australia, South America, all over the planet after having been dumped accidentally in one place up here in the North Pacific. So that one place caused ducks because that one place was located where it was, or whatever the case is. The ducks were able to make their way all around the Earth, and so this would have been a great example if these were living things of eventually become an index fossil if they all died and were buried at the same time. Very widespread and short-lived is how we define index fossils in the rock record. But alas, rubber duckies are not index fossils or living things. But nevertheless, they did a nice job of illustrating how ocean currents work. Now, air masses are, of course, a result of those Hadley cells moving around, but also the moving around of the air by the Coriolis effect, and then, of course, the interactions with the oceans. So these air masses will move around. They create and in part they create because things like the jet stream were created, which are these rivers of air, if you will. They're like ocean currents, but air currents that occur aloft, well above our heads, and they will typically separate air masses. Particularly the jet stream is particularly separating colder northern air masses here over North America with, so let's just say warmer air masses to the south. And the position of that jet stream will often dictate what kind of weather we are to expect. But these boundaries between air masses, what we call fronts. So like this might be this is still a cold air mass, and this is still a cold air mass, but this could still be a cold front because the temperature differential may be enough to call it that. This would be a warm front, or it could be a cold front, depending on the perspective. So there's some other variables to invoke here, but still, boundaries between air masses are typically called fronts. Fronts come in a variety of forms, 4 to be specific. Cold fronts and warm fronts are the basic ones. Cold front is simply where a warm air mass is being undergirded by a cold air mass or subducted beneath by a cold air mass. And these cold fronts tend to actually happen pretty rapidly and move warm air up really rapidly, which ends up creating a lot of condensation and really big clouds called thunderheads, and then you get thunderstorms. Warm fronts are more gradual, and the warm air mass is still moving on top of over the cold air mass, but it's much more gradual. You will get rain, but it'll just be rain. It won't be big thunderstorms. Then there's occluded fronts where you'll have a cold air mass and a cooler air mass interacting at the surface, where you'll have warm air on top, and you can still get rain, of course, with that. And then stationary fronts where where you have a cold air mass and a warm air mass, but they're not necessarily going anywhere. And so here's a depiction of the jet stream. These boundaries between air masses that I was just mentioning a little bit ago, courtesy of NASA again, an animation of it. So you can see what these boundaries look like. Again, that's the jet stream. That's the river of air that often separates things. You can see what's happening here. Warm air is moving up into that pocket there. And eventually, now it's cooler down here. Cooler air moving further south. So, of course, the models, all the forecast models have to take into account the complexity of that river of air. You can imagine how challenging that is. Now, of course, all of this moves around water vapor, of course, as well. Water vapor moving around leads to cloud formation. I already mentioned thunderhead clouds, and you have those over here. These lead to severe thunderstorms, and, of course, hail and other things with that. As you move that air upward and drop the pressure, you end up with big clouds and very violent thunderstorms, along with tornadoes as well. You're going to have clouds way up aloft, up in the stratosphere, up near the boundary of the stratosphere, and some of them are going to be crystals, ice crystals up there. So you'll have floating ice, if you will, up in the atmosphere. And so some of these are different altitudes. These high altitude clouds, sometimes they mean if they're coming in and you got a haze around the sun or around the moon, that may mean that there's, at least in our latitude, that may mean that there's a front or some rain coming, because you got moisture kind of making its way into the upper atmosphere, which means that following it may be moisture at lower elevations and so forth. There's no, that's a sign, right? It's some of the way the forecasting used to be done many, many years ago. We would use signs like that to help us out, and they still play out today very, very generally very accurately. But clouds are one of those things that are hard to model, so we have to do the best we can. Scientists have to do the best they can modeling them, because they can both reflect energy and they can also trap energy in below them. So these are things that we have to take into account. But of course, they're much more than just the things you look up like laying on your back out in the field and enjoying the picture of a bunny rabbit flying across the sky. They're much more than that, of course. Then there's El Nino and La Nina. There are global weather phenomena that have significant impacts all over the place, or I should say, regional weather phenomena that will have impacts beyond their own local. So El Nino is a change in the southern oscillation, where the sea surface temperature changes significantly, and you'll have typically along the coast of South America over here, you'll have nice, cold, nutrient-rich waters, and the fishing is great. And then one year, for a little while, for a year or two, there'll be really bad fishing because now you've got water that's moved in from out in the Pacific that's now warmer, and the warm water doesn't have the same nutrients it has in it. So here you have upwelling along the coast of South America, where you have that cold bottom water that's rich in nutrients, that's coming up, and it travels back out to sea. Here, that upwelling gets reversed to downwelling along South America, and the water is being brought back by winds that are moving the other direction across the Pacific. And of course, you can see what happens to the coast of California here. You end up with warm water over here as well along the North American coast, versus during a La Nina period, which are the periods opposite El Nino, as you can see down here. While one's occurring, the other one's not, and vice versa. You can see that the waters along the west coast of California are behaving differently as well, including the Gulf of Alaska. And of course, that ends up affecting our weather here in Virginia also. So you'll hear weather forecasters talk about it being an El Nino year or not. And they take it a whole lot more seriously than they did when I was a kid, because back when I was a kid, they didn't know much about the phenomenon. So now that they know more about it, they know how to work it in. But of course, this has always affected fishing in these regions. And there's been this pattern has been around, which is where the name comes from. El Nino means the child, and it's typically associated with Christmas time and so forth. And it comes from culturally, it comes from a people who know something about the fishing industry and its ups and downs due to these phenomenon. All right, so then there's, of course, it's important for us to study severe storms a little bit, hurricanes and tornadoes in particular. So here we have a cross section of a hurricane using the TRMM precipitation radar, and you can see that hurricanes are quite thick in terms of their elevation profile from the surface up to the upper troposphere, and then of course they occur in a circular pattern in the shape that they of course are as they're spinning around, I should say. And of course here these are thunderstorms producing tornadoes across the mid-south in the U.S. Of course, these are areas, Kansas, Oklahoma, Texas, that will typically have thunderstorms and tornadoes more commonly than other places because they're so flat and because the thunderstorms really have enough space to develop. Now, we do get tornadoes here in Virginia, perhaps more prevalently than we used to. I don't have any data on that right now, but it'd be worth looking into. I grew up in Ohio, and we had lots of tornadoes in Ohio. In fact, there's a famous one in Xenia, Ohio, in the early part of the 20th century there. The tornado was a mile wide. Just last year, we had big tornadoes in Dayton, Ohio, in fact, a big outbreak. Caused a lot of damage. So that may date this presentation now a little bit. Hurricanes in particular are giant low-pressure systems that have, of course, a certain construction. They look like a big cyclone because they're an anticyclone, or they're a low pressure system, and they are in the center. That low pressure is actually causing air to descend through the eye, and of course, when you have descending air, you don't get clouds. When you have ascending air, you do. So the air around the eye is rotating. That rotation is a result of the movement of the storm along the front that's formed along. And that air is all moving up, while the air in the middle in the eye of the hurricane is descending downward. Now, the hurricane itself is being fed by the warm ocean waters, and that's the primary energy source for the hurricane. So really, ultimately, the sun is warming the oceans, and then the oceans feed the hurricane. So the warm, moist air is rising along the outer bands, and that's where all the rain is occurring. And that's also because of the winds and stuff that are moving around it with the hurricane, and they're really, really fast, of course, because they're now they're now much more focused, and the energies actually, there's a lot of energy being pulled out of the ocean, which then leads to higher winds and so forth. Those higher winds then drive storm surge, which is basically the pushing of the water onto the seashore. And the storm surge is actually the biggest problem with hurricanes, much more so than the wind. Now, the wind is a big deal, but storm surge is the biggest problem. That's actually what causes more damage than anything else. All right, but it's a big storm full of rotating winds, and of course, depending on where you are in the hurricane, we're talking several hundred miles across, is going to determine what kind of effects you're going to experience. So, for instance, for those folks where the hurricane hits up here, you're going to get a lot of storm surge because you got a lot of winds just lashing and being, lashing along the coast and being. I'm talking about the North American East Coast, and that's pushing the water up against the seashore. Where the storm surge over here, let's say this is North Carolina over here, the storm surge over here is actually causing to push the ocean out to sea. So you may actually see a negative storm surge in some places. And so you have to be very careful when you're in a hurricane like this. If you're gonna try to ride out the storm, as some people do, you got to really be really careful how you're hunkering down and where the storm is, and in terms of its proximity to you. So a hurricane forms primarily from the evaporation of water. The moisture rises, creating thunderstorms. Okay. If you have low wind shear, meaning that the wind is not actually interfering with the hurricane, it's actually moving right along with the hurricane, then you're able to get it to form. The winds are going to spiral upward and outward, and then, of course, at the center, a low pressure system forms over the ocean surface. Then you're going to get clouds forming in the upper atmosphere as the warm air condenses. As that warm air condenses and those clouds form, the storm is able to gain even more strength. It pulls more energy out of the oceans. When the storm passes over land, of course, it loses its supply of moisture and heat, and the storm is going to gradually dissipate. Now, they start off as tropical depressions, reach the tropical storm status at a particular wind speeds. I forget the exact thrust. It's 76 miles per hour, I believe. And then they move to a Category 1 hurricane, Category 2, Category 3, Category 4, and Category 5. But eventually the entire storm starts to spin counterclockwise or clockwise, depending on the hemisphere. Because, of course, you can have, quote-unquote, hurricanes in the southern hemisphere, but we refer to them as cyclones. 74 degrees, here we go. Category 1 hurricane is born at 74 miles per hour, not 76. So warm ocean water with a sea surface temperature of at least 80 degrees Fahrenheit is necessary. And so you see the Gulf of Mexico over here. These temperatures are in Celsius, but these are the perfect temperatures for hurricanes to really gain steam. And typically a hurricane is going to come off of the west coast of Africa. That storm will make its way across, eventually becoming a tropical depression, eventually becoming a tropical storm as it gets into the warmer waters. Then as it moves into the Gulf of Mexico or moves up the east coast, whichever way it goes, it'll begin to gain more steam or not, and eventually move on to land. And this is in the northern hemisphere. This is typically where hurricanes move from the west coast of Africa on towards North America, and then off of the west coast of the U.S. out to the Pacific. And in the southern hemisphere, cyclones, as we call them, or I should say, these hurricanes, we call them hurricanes here. We actually call them typhoons in the northern hemisphere when they are coming out of the Central Pacific and across Asia. Now, in the southern hemisphere, primarily in the Indian Ocean, we call them cyclones. They can occur over here. They can occur, and so they tend to be pretty big storms. Here, these typhoons can be really, really big. We had a couple of big ones a couple of years ago. Typhoon Haiyan and some others have been really big of late. So now, attributing any particular hurricane season and its intensity to global warming, of course, is doable, but it takes a lot of work to do that. So we do see that they do tend to be intensifying over time, which is one of the predictions that would be consistent with global warming. How about this storm here? Has been staring at you as the background for this presentation the entire time, and these lovely tornadoes. Tornadoes are like a micro hurricane in a sense, except they're not a hurricane. And they form in conjunction with thunderstorms, particularly big tornadoes with supercell thunderstorms, which are really broad thunderstorm systems. And, of course, again, you have a main updraft, all right? And then, of course, you have downdrafting winds as well around the hurricane. And of course, this interaction between the updraft and the downdrafts produces a rotational vortex that makes the tornado. And of course, there's also in the center of the tornado, it's a major low pressure system. So much like a hurricane, the air in the middle of a tornado is actually traveling down and then traveling back up along the outside of the tornado as it's spinning. And of course, that's what causes all the debris and the high winds. And you don't want to be in the way of one of these things. These things can have wind speeds that are well above hurricane force. They're just much more compact. One single thunderstorm, however, can spawn many tornadoes. If it's really big, it can spawn tens of tornadoes. And tornadoes can be short-lived, like touch down once and go away, or they can be long-lived and travel for tens of kilometers or more across the land. And the best tornadoes are the ones that travel across open land. The worst are the kinds that travel and hit schools and towns and things of that nature, like Dayton, Ohio, a couple of years ago, among many other places. So tornadoes are definitely something you don't want to get in the way of. This was back in 2015. All the outbreaks of tornadoes that were reported during that year, and you can see where most tornadoes are reported is certainly across the U.S. Midwest, the Plains states, including from Minnesota on down to Louisiana and so forth, but even over into Illinois and Indiana and the deep South as well. And of course, Virginia, we have a few outbreaks of our own. In fact, I remember just a few years ago, and I forget what year it was, maybe it was 2014, the year before this one, we had a tornado touchdown in my house in the Shenandoah Valley, jumped right over my house. But there we were huddling down underneath our stairs with a small child and a baby. It was a pretty scary moment. And having grown up in Ohio, I mean, they've had tornado warnings and watches all the time, but had to move down to Virginia to actually have one come close to hitting me, which is strange because we have fewer of them in Virginia than we did in Ohio. All right, well, that takes you to the end of this presentation. I hope you enjoyed it. Again, direct questions, as many as you can to your master teachers. They're there to help you. Otherwise, I hope you enjoyed watching. Until next time.